Subscribe and click the notification bell to stay updated with the latest videos from School of Technology, Management and Engineering NMIMS in
A very good afternoon to everyone present here. Today, I, Darshika Ajmera, on behalf of NMIMS School of Technology, Management and Engineering family Indore, takes immense pleasure in welcoming you all to the AICTC Training and Faculty Development Program on Internet of Things. Before we move ahead, I would like to inform you all that a feedback form will be floated in the chat box, so please fill the necessary details correctly as attendance will be provided on the basis of the submission of feedback forms. So, the topic for today's session is IoT analytics. IoT has gradually transformed the way daily tasks are completed. In doing so, cloud computing has been a great help. On one hand, IoT generates a lot of data, while on the other hand, cloud computing paves way for this data to travel. Furthermore, IoT and big data analytics are transforming how businesses are adding value by extracting maximum information from data to get better business insights. To throw some light on this, we have with us Dr. Lalit Singh. Dr. Singh received his PhD degree from Indian Institute of Technology and is a scientist in NPCIL BARC Department of Atomic Energy, Government of India since the last 20 years. He is a recipient of many awards like the Publication Award, Group Achievement Award, etc. He is a life member of Indian Nuclear Society. He is a founding member and industrial coordinator of the proposed Center of Dependability at IIT BHU. He is also a faculty of Nuclear Training Center, Department of Atomic Energy, Government of India. He is interfacing with other countries like Russia, USA, France, etc. for important nuclear reactors that are based on new technologies. He holds 628th rank in India in the world list of scientists released by AD Scientific Index. We feel privileged to have you today with us, sir. I now request, sir, to share his valuable inputs with the audience.
Thank you, Dr. Darshika, for the introduction, and I would also like to thank all the organizing committee members who has given me this opportunity to share some of the research experience to all the participants. So to start with, let me share my slides. So I hope the slides are visible.
Yes, sir.
Yeah, thank you. So I'll be talking on reliability analysis of safety critical IoT systems. And to start with, I would like to touch upon the topic, the essentiality of this topic, so that a motivation can be drawn about this topic. And so to introduce this IoT systems, these are the distributed systems, and distributed in the sense there are several processing nodes, and these processing nodes are maybe remotely located, and maybe they may be exchanging the data through the internet, and hence when because this processing nodes definitely process the data based on the input that it received. So the exchanging the information, the correct exchanging of information also plays a very important role. So, and especially these, many of these IoT systems are safety critical in nature. Safety critical in the sense, safety critical systems are the systems, the failure of which can lead to the catastrophic disasters, or even it can lead to the loss of human lives. And there are the wide range of applications where we make the use of safety critical systems, where we make the use of safety critical systems. For example, in the field of medical domain, the nuclear domain, military domain, defense domain, automobiles, and so on. And hence, they do have a very high reliability requirements. But if in terms of like engineering, until we don't measure the thing, we cannot gain much confidence. So here I'll be discussing how we can quantify the reliability of such kind of IoT systems. So when I talk about the reliability, it can be defined as the probability of the failure-free operation of a system up to a given period of time under certain environmental conditions. And this definition is very important, and each term is very meaningful. So to understand the definition, as I said, it is the probability of the failure-free operation of the system. It means its value ranges from 0 to 1 if I talk with respect to the quantification of the reliability, because the value of the probability ranges from 0 to 1. And 0 means the least reliable, and 1 means the highest reliable. And the probability of the failure-free operation of the system. Failure-free means success operation of the system, and up to given period of time. It is very important to tell up to how much period of time we are talking about anybody's reliability, because nothing is reliable for the infinite period of time. So you also have to state or mention the target time. So then in the definition, I use under certain environmental conditions. So under certain environmental conditions is a very important, because one product may be very highly reliable under one environmental conditions, and may be very less reliable under other environmental conditions. The same product. So the environmental conditions or the operating conditions plays a very important role. For example, suppose you go and bring the refrigerator, and you get a warranty period of 1 year. But when you come with the refrigerator in your home, and suppose you throw it from 12-story building, it will collapse, and then you cannot go back to the vendor and ask for the replacement. But he will say you have not followed the operated conditions, the stated operated conditions, and hence your warranty has been voided. So the two conclusions from our discussion can be brought out, that reliability is a function of time, because we also have to mention up to what period of time I'm talking about, that is known as the target time. And the second one, it also depends on the operating conditions. So let us have the outlines of today's talk. So introduction to reliability, I have already discussed a lot about its background, but yes, we can see the mathematical representation of the reliability, because ultimately we have to deal with the quantification of the reliability. And then I'll be discussing a mathematical formalism known as PetriNet. And this PetriNet is basically a graphical and mathematical tool, and the concept was introduced by C.A. Petri in 1960s, who was a German PhD scholar. And he introduced this concept to model the stochastic processes. So if I want to categorize the processes, I can do it into two categories. One is the deterministic process, and the other one is the stochastic process. So the deterministic process, the processes, the outcome of which can be 100% guaranteed. For example, suppose I do have a pen in my hand, and if it slips down, it will definitely fall on the earth. Why? Because of the gravitational force that is acting on it. So I can say like it is a deterministic process, because I am 100% guaranteeing the outcome of this process. While the processes whose outcome cannot be 100% guaranteed in spite of the rigorous planning or the systematic approach. Such processes are known as stochastic processes. And for example, suppose I need to catch a flight to attend a meeting at Hyderabad in 4 p.m. at 4 p.m. So considering all the local traffic delays, the flight delay and the local traffic at Hyderabad, and also considering some amount of overhead, I am suppose I start here at 11 a.m. and but to catch a flight at 2 p.m. or something. But then also I may miss my target. The reason could be manifold. One reason could be, suppose I'm taking the normal route to start from my home to reach to the airport. But when I was about to reach the airport, just I was 1 kilometer ahead, I came to know like there is some road construction that is going on. And because of this road construction, I have to take some alternative path, and which is quite longer, and it is very crowded also. And then in that case, I may miss my flight, or suppose if I reach the airport on time, I could find like there's a flight cancellation or excessive delay in the flight because of some technical or administrative reasons. So I wanted to make a point here. Although the probability is very less when you pursue the things in a very systematic approach, but you cannot 100% guarantee, you cannot nullify the probability. You can only minimize the probability. And in fact, the human is also stochastic in nature. So whatever the systems that have been developed by the human definitely will be stochastic in nature. So PatriNet is a very good formalism from which can capture the dynamics of the system or the stochastic behavior of the system. So we will discuss about the working mechanism and the basic building blocks of the PatriNets, and also we will be discussing the properties of the PatriNets, which are important to analyze to know more and more insights about the systems, and what are the various analysis techniques. And then I will be introducing a reliability prediction framework in which I'll be discussing all the phases that are required to be executed for the quantification of the reliability. And I'll be also discussing each and every activities that needs to be performed for the completion of this particular phase. And then I will take a real case study where which I will be using for applying this prediction framework, and we will see how we can quantify the reliability, and then we can conclude our session. Yeah, so if you talk about the mathematical representation of the reliability, so suppose X is a random variable, and that represents the time to failure of a component. It means it represents how much time a component is taking to get fail. And then so clearly what does it mean if I'm taking a target time t? So definitely this time to failure must be greater than target time to ensure the reliability of my product. So the reliability of the component at the time t can be given by rxt. As I told you, it is a function of time, and it will be equal to probability that the value of this random variable x must be greater than t. And from the total probability law, we can equate it to 1 minus probability that the value of x will be less than or equal to t. And where the probability that x is less than or equal to t, it represents because it represents that your component has failed before this target time, and hence it represents the failure probability. So we can write it down as equal to 1 minus failure probability, which is also a function of time, and failure probability can also be termed as the unreliability. So now I will be discussing about some of the traditional methods that are being used for the quantification of the reliability. And the one of the prominent method is a model is known as a reliability block diagram, which represents the logical structure of a system with regard to how the reliability of its components can affect the system reliability. So what does it mean? For example, your system contains two components, C1 and C2, and having the reliabilities R1 and R2 respectively. And these components can either be arranged in series or can either be arranged in parallel. So the reliability of the overall system can be computed by applying the series or parallel reliability formula. If they are arranged in series, we can use the series reliability formula. So for example, if the two components having reliabilities R1 and R2 respectively, then the overall system reliability will be R1 into R2. And if they are arranged in the parallel, we can apply the parallel reliability formula. And in this way, we can quantify the reliability of the overall system. Now the question is, from where we will get the reliability of the basic components. So the basic components reliability can be derived from the statistical data and the words experience. And if you look, there are several catalogs available in the market. For example, if you are dealing with the electronic systems, you can find the mill handbook where the failure or the reliability of each and every electronic component is mentioned. For example, or if you are dealing with the mechanical systems, there is a ASME handbook catalog you can find from there, and accordingly it can be assigned. And now there is one more model known as a reliability graph, which is similar to the reliability block diagram, which consists of the set of nodes and the edges, where nodes are used to model the link between two components, and arcs are basically components itself in the system. So if you look the pictorial representation of the reliability graph, this slide, the left figure in this slide shows the reliability graph, and which you can see like it contains the nodes having A, B, C, D vertices, and each of these vertices are representing the connectors, and all the V's which represent edges are the components itself. And so it can easily transform into the reliability block diagram into equivalent reliability block diagram as given in the right figure of this slide. So you can see like every V starting V1 from V1 to V5. All these are the component itself which have been written like this, and all the vertices A, B, C, D's are the connectors between these components. And in this way, now if suppose the reliability of these components are R1, R2, R3, R4, and R5 respectively, then you can see 1 and 4 are in series, and you can compute the reliability of this segment. It will be equal to R1 into R4. And similarly, 2, 1, and 2 and 5 are in series. Again, you can apply the series reliability formula to compute the reliability of this segment. And then you can see all these three segments, 1 and 4, you have already solved, and then segment 3, then 2 and 5 you have solved. All these three are in parallel, where you can apply the parallel reliability formula for computing the overall reliability of the system. And one more prominent model is known to present all the sequences of individual not working. So this will be the root, and then gradually I will have to try, or I will have to deduce the reason, and I will be then finding the root cause. So the cause could be, it can be electrical failure, or could be mechanical failure, or it could be electronics failure. So considering like electrical failure, that may include the failure of adapter, or the failure of the socket from the laptop side, or the power supply is not coming, or there is a loose connection at the power supply side. These could be the reasons basically. So in this way, we can derive the root causes till we reach to the basic event, and we can assign the failure of these basic events from the statistical data. And if those basic events are arranged in AND logic, so suppose if I say any human is not able to see, so the root cause could be his left eye is not working and right eye is not working. Then if the probability of the failure of left eye is P1 and right eye is P2, and because they are arranged in the AND logic, then the probability that human is not able to see will be P1 into P2. So if they are arranged in the AND logic, we have to multiply the failure probabilities. If they are arranged in the AND OR logic, we have to sum up the failure probabilities, and ultimately we can deduce the top level failure probability, and which is the system failure probability. And we have already seen that the reliability of the overall system will be equal to 1 minus failure probability. So you can subtract it by 1 to compute the reliability of the overall system. So anyway, so these are the traditional models that we have discussed so far, which are the fast models because it uses the fast algorithms, and but it assumes the stochastic independence between the system components. This is very critical. What does it mean? It means like if suppose one system contains 4 components, C1, C2, C3, and C4, I have to assume like C1 and C2, all these components can fail because of their own reasons, and nobody can impact their failure. But it is, in reality, it is not. One component maybe fail because of the other component getting the wrong data, or which is not expected, and hence it may be possible that it may fail either independently or dependently, means with that is dependent on the other component, either directly or indirectly. So this is stochastic dependence. If you want to show, or if you want to model, or these such kind of complicated interactions between the components, we must use other kind of models like Markov chains and all. So if you look into the Markov chain, these are the most powerful tool for the reliability and safety analysis, because they provide modeling capability for all sort of dependencies. And it also have a capability of the capability to demonstrate the stochastic behavior of the processes. And if you talk about the conceptually, the concept was introduced by Andrew Markov, who was a Russian mathematician in 1940s or early 19th centuries. And He thought of why don't we treat any process or any system in terms of states. For example, human is a system. Human can have various states. It can have reading state, laughing, talking, walking, sleeping, eating, and so on. And these states could be normal behavioral states or could be failure states. And a failure state, for example, if anybody is meeting an accident, that will be considered as failure state. And so basically, if somehow we are able to find the probability of a system being in all the success states or all the normal states, and if you sum up those probabilities, that will give the quantification of the reliability. The other way out, if we are able to find the probability of the failure of the probability of the system being in failure state, that will give the system failure probability, and if you subtract it by 1, it will give you the reliability of the overall system. So if you look into the basic building blocks of this Petri net, that includes the states and the transition probabilities among the states. And the transition probabilities can be derived from the statistical data or for the similar kind of projects. And now let us have a look on some of the mathematical concept in Markov chain, which we definitely will be using in our prediction framework. So for example, there are the two states I and j in the Markov chain, and let Qij be the transition rate from state I to state j. Then we can define the transition rate from state I to itself. That will be equal to minus, and we have to sum up all the state transition rate from state I to rest of the states. And this is what this formula is. And then I introduce a terminology known as the transition matrix or the generator matrix. As it is a matrix, it contains rows and columns where you can write the rows, the number of states in the rows and the same number of states in the columns. And then you can fill in the elements with the transition rates from one state to the rest of the states. And so this will this form matrix will be known as the generator matrix or the transition matrix, or you can say the transition rate matrix. And okay, this is the Petri net, and it is as I said, it is a graphical and mathematical tool. Why graphical tool? Because we can simulate the entire process of the system, and all the stakeholders can come to know the behavior of that system, the function of that particular system. And why it is a mathematical tool? Because it uses we can embed the mathematical knowledge, and we can derive many of the state equations or algebraic equations to know more and more insights about the system. So it is the best communication between the theoreticians and the practitioners. So if you look into the history of PatriNet, starting from its origination to some of the important milestones that it has achieved. So as I told you, the concept was introduced in 1962 by C.A. Petri, who was a German PhD scholar, and he introduced this concept to capture the dynamics of the system. And looking at his thesis, the people started taking interest, and there was an era where the people were working for the parallel systems or the concurrent systems. So in MIT, USA conducted a conference on concurrent systems and parallel computation in 1970 with an objective to know whether this model can be useful to model the parallel or the concurrent systems. And the conclusions were very fruitful, and the researchers were trying to strengthen the model. And with this objective, again, they decided to meet after 5 years. So in 1975, MIT USA again conducted a conference on Petri nets and related methods. And thereafter, it started gaining the popularity in the industries, and looking at the industrial demand, Germany started a course on general net theory of processes and systems in 1979. And then the people from different domains were also, eager to understand whether this model can be useful to model their particular kind of application. And with this objective, in 1980, the first European workshop on applications and theory of Petri nets were conducted. And then the people were coming out with a different flavor of the Petri net. So, for example, if you want to work on the real-time system, definitely it should possess the feature where you can embed the timing information and you can solve, the related attributes. So this is specialized Petri net. The researcher has come out with a specialized Petri net known as time Petri nets, where we can embed all these the timing information. And so the first international workshop on time Petri net was conducted in Italy in 1985. So although this is not an exhaustive list, but it contains but it tells about the origination of the Petri net, and along with some of the milestone that it has achieved, by which it gained so popularity. And if you look into the Petri net modeling, so suppose I'm taking a very small example for the concept building. Suppose you want to model a very small chemical reaction, that is hydrogen and oxygen that transforms into water. We all have studied in class 9 or 10. Now you want to model. So first, before discussing the model, let us try to understand the basic building blocks. So the figure that you are able to see is basically the model of this chemical reaction, the left-hand side of this chemical reaction. And so looking at the basic building blocks, you are able to see there are the 3 big circles in this figure. And these big circles are known as places. And I'm using places to represent hydrogen, oxygen, and water. And then there is a rectangular bar. You can see so this rectangular bar basically is known as transition. So the places can be connected to transitions, and transitions can be connected to places by the directed and weighted arc. And for example, the weight of the arc connecting hydrogen and transition T is 2, and the weight of the arc connecting oxygen place and transition T is 1. So I have not kept any weight. So when I don't keep any weight, by default it is treated as 1 notationally, or otherwise explicitly you can put a numeric number 1. And I will be discussing the significance of this weight while I'll be discussing the working mechanism. Then the next building block, you are able to see the small embedded circles inside the places. For example, hydrogen contains 2 small embedded circles, and these are known as tokens, and you can represent a token depending on your context. So for example, here I'm using tokens to represent the number of atoms in the hydrogen because it is diatomic, and so only the 2 tokens I have shown. Similarly, the oxygen is also diatomic, so only 2 tokens have been shown. And then so one important fact is that the distribution of the token basically represent the state of the system. So you can see here the distribution of the tokens among the places are 2 to 0 because hydrogen place contains 2 tokens, oxygen contains 2 tokens, and water contains 0 tokens. So 2 to 0 is the state of this system. And because it represents the left side and now it has to convert into the water, so it means we need to change the state of the system. But so for changing the state of the system, we need to change the distribution of the tokens. But the distribution of the tokens can be changed only if at least one transition must be in enabled state. So because here you can see there is only one transition, and this transition must be in enabled state if I want to change the distribution of the tokens. But what is the criteria that your transition is in enabled state? And the criteria says that all its input places must contain sufficient number of tokens. So all its input places, it means for this transition, the input places are hydrogen and oxygen. And because the arc are emerging from these places and terminating on the transition. So it is connected by the, but these places are connected by the input arcs, and so these are the input places, and it must contain sufficient number of tokens, and the sufficiency of the tokens will be governed by the weight of the respective arc. So if you look in this figure, the weight of the arc connecting hydrogen place and transition T is 2. So it means hydrogen place must contain at least 2 number of token. And similarly, the oxygen, the weight of the arc connecting oxygen place and transition T is 1. So oxygen place must contain at least 1 number of tokens. And so this criteria fulfills here, and hence the transition is in enabled condition, and when any transition is in enabled condition, it fires. And after firing, the movement of the movement of tokens from input places to output places occurs. But how many tokens will be moved out from the input place and how many will be deposited into the output place, that will totally governed by the weight of the respective arc. So here again, you can see the weight of the arc connecting, hydrogen place and transition T is 2. And the weight of the arc connecting oxygen place and transition T is 1. So hydrogen place must contain at least 2 number of tokens, and oxygen is 1. And these many tokens only will be moved out. So 2 tokens will be removed from the hydrogen and 1 token will be removed from the oxygen. And how many will be deposited into water? On the 2 tokens will be deposited into the water place. So that will also be governed by the weight of the output arc, which is 2. So one interesting fact, you can see like there is no law of conservation of the token. You can see like this is now the situation where the 2 tokens has been moved out from hydrogen place and 1 from oxygen place, and 2 has been deposited into the water place. So there is no concept of the conservation of the tokens. So because if you sum up the total number of the tokens in hydrogen and oxygen, it will be 3. It is 3 that has moved out, and the total number of tokens that are deposited in the water place is 2. And now one interesting thing. So this state is 0, 1, 2. because the token distribution is now 0, 1, and 2. So earlier it was 2 to 0, and it has, after transition T, it has changed to 0, 1, 2. And one interesting fact is that here, okay, before that, you can now see again the enabling condition of the transition. So you can see now this transition is not at all in enabled condition, because the criteria says that all its input places must contain sufficient number of tokens. So input places are hydrogen and oxygen, and both must contain sufficient number of tokens. So here hydrogen is not containing sufficient number of tokens, which should be 2, considering the weight of the arc connecting hydrogen and transition, and while oxygen is connecting sufficient number of tokens. But it is AND logic, it is not an OR logic, and hence now the transition is not in enabled state. So your system state is going to remain same. This is the final state. So one interesting fact is this Patrinet is also helping you to identify the state space of the system. So earlier it was, so here I want to introduce a new terminology known as reachability graph. So if you say the reachability graph, as it is a graph, it contains the nodes and the arcs, and nodes represent you know, the states, and states are nothing but distribution of the tokens, and arc represents the transitions which are changing one state to another. And again, you know, the different nodes will be there. So here in that reachability graph, particularly with respect to our this example, it will be 2, 2, 0, and then after transition it will be 0, 1, 2. And then I need to, after that, okay, I need to touch upon some of the basic concepts of the Markov chain. So in the Markov chain, I mean, we all know it contains the states and the transition probability between the states. So for example, the figure that I have shown, it consists of 2 states, S1 and S2, and the transition probability that is transiting from S1 state to S2 state. And then suppose there is a random sequence of random variables, x1, x2, x3. So what Markov property basically says that the next state of the system will always depend on the current state of the system and not on the previous state. And what is this mathematically we can represent? So it is like probability that the value of that the system is in n plus 1 state is x. It will be only you know, depending on what is the value of my system that it was in nth state, and not on the previous state. So you can equate it is equal to probability xn plus 1 is equal to x, given xn is equal to xn. So all the x1, x2, x3 you can discard. And this is just a random slide just to show how we can represent the reachability graph. So suppose there is a Patrinet figure, a graph or model which contains 7 places having the tokens, initial token 1001010, So what does it mean? The first place contains 1 token, the second place contains 0 token, and so on. And then this is, as I said, the token distribution is known as a state, or in Patrinet terminology, we can term it as marking also. So I have represented by M1. And suppose after firing of transition T1, it is transiting to M2, and after firing of T2, it is transiting to M4, and so on. This is just a imaginary example, just to show how we can represent the reachability graph, and we can transform it into the Markov chain as shown in the right side, because each marking is nothing but it is a state. And so the state in Markov chain are represented by the round circle. So all the 1, 2, 3, 4, these are the states, and these are the transitions. So transition probability is lambda 1 or lambda 2. These are all the transition probabilities of these transitions, and this is how we can transform the Patrinet into its equivalent Markov chain that we have seen. And now I'll be introducing our reliability prediction framework. And so our framework contains the 3 phases. And in the first phase, we have to create the Patrinet model. And in the second phase, you have to convert it into the Markov chain. And in the third phase, you have to compute the reliability. And the first phase have already been discussed. The second phase also we have discussed but definitely we will take a case study in which again we will be seeing how we can create a Patrinet model and how we can transform it into the Markov chain. And the third phase we have not discussed, and we will be discussing it, like how we can solve the reliability by applying the mathematical concepts. So before I discuss the case study, let me introduce you some of the mathematical concepts that are necessary to know, which we are going to use in our particular model. So suppose pi it be the probability that a component is in state I at time t. And where I can be the failure states or the behavioral states. We have already discussed a lot on these states. And when t goes to infinity, so it is these probabilities converge to the stationary distribution. This is very important concept, and you should know you all should know that it clearly, it only says when your system is very small, its complexity is very low, and when your system is very big, its complexity is very, very large. For example, suppose you fill a glass of water, and you will see and just put it on the table. You will see initially the water will be very zigzagging, and after a certain period of time, T1, it is settling down. It will settle down after some period of time. But if you just try to replace the small graph with a huge container, probably at the size of your room, so what you will have, and suppose you fill it with water, and you may lift it by a crane and put it somewhere, you will find that initially the water will be very zigzagging, and it will take very, very long time to settle down as compared to the time taken by the glass. So what I want to emphasize on the fact is, when your system is very complex, your this complexity of the system will be more, and hence it will take a long time to settle down. So theoretically, I have assumed like where t goes to infinity, all these probabilities, stationary probabilities, right, when converged to the stationary distribution, and which can be computed by the two equations. One is very simple. It clearly it's only says that the sum of all the state probabilities of a system at a time will always be equal to 1. That is but natural because of the total probability law. And the second equation is also very simple. Let me explain with the help of the same example as we have taken in the huge container. So you can see like in the huge container, initially the water will be very zigzagging. And suppose this state is S0. And suppose after T1 time, it is propagating towards settling process. And settling process in the sense, so it is, it is changing the state, and suppose it has reached a state S1 after T1 time. So, it will depend on the S0 into the transition probability from S0 to S1. And from further S1 from to S, suppose it reaches to S2 state, which is more, will remain same because it has already settled down. Then Sn plus 1 state will be Sn state only, but the equation will remain whole same. That is Sn plus 1 is equal to the Sn into the transition probability from Sn to Sn plus 1. And this is what this second equation is. So this is the final state, which is going to be the previous state, and you have to just multiply it by the transition probability. And these two states are important, which we will be using to derive the reliability. And now let us discuss a case study where we can, apply our framework. So suppose there is an IoT system which are having two processing nodes. One is, for example, capturing the data from the field sensors, that is the embedded unit, and it also process that data, and after processing it is sending the data to the other processing node. And this is known as, for example, display unit, which is just displaying your data. And suppose I want to, because it is exchanging the important information, and I want to understand, or I want to evaluate the reliability of this communication. So first, let us try to understand what is the communication protocol that could be followed. So the communication protocol that we have adopted is in the similar lines that if I want to call a friend, so when I want to call, I just dial his number and wait for his pick, and if I don't get, then and wait for the acknowledgement. Basically, if I don't get the acknowledgement again, so before acknowledgement, but when I will dial, if suppose it rings, and then if he lifts up, then I will say hello, and then I will wait for the acknowledgement. But if I don't get the acknowledgement, I will assume that there is some connection problem. I will again say hello, and I will keep on saying till I get the acknowledgement. But up to how much period of time I should try? For example, if I'm not getting the acknowledgement even after 5 to 6 or 10 times, then what I will assume that there is a loss in the connection, and there's a permanent that I should cut the call and I should retry the call. And then I can again try. And if it gets connected, then I will assume, okay, the connection has been established and now I can start my conversation. And the similar protocol basically we have implemented here. So suppose the embedded unit, it sends a new packet. Then the value of this, it is keeping a trace of how many packets, how many times it has sent the packet, the same packet. So the same packet means we have to append the sequence number in each packet. And that is also very important because the packet which has been sent from the source in some predefined sequence, in the same sequence, it needs to be arranged in the destination for the proper interpretation of the messages. So whenever embedded unit sends a new packet, I'm first setting a count variable to 1, and then embedded unit will wait for the acknowledgement for suppose t1 time after sending the packet. And if embedded unit receives the acknowledgement before t1, the packet sent will be successful. And I'm keeping a semaphore variable new si, it will change to its complement. So if the count is less than n, count is less than n means I have tried for n number of times and still I'm not able to connect it. So if the count is but if the count is less than n and acknowledgement is not being received, the embedded unit will again retransmit the packet and sends the count and increment the count. Otherwise, the embedded unit will terminate the send process unsuccessfully once the count reaches to its maximum value. And in this case, the semaphore variable new will not be changed, and if t1 elapses after last data sent, the new is destroyed. And now I have to create a Patrinet model of this communication protocol, as it was our first phase. So this is the Patrinet model, and interestingly, you can see the weight of all the arcs are 1. And let me explain this model. So you can see, like at the initial point of time, there are the tokens in 2 places. One is PSRDY0, that represents that you have, or U means embedded unit is ready to send the packet with sequence number 0. And the other one is PDSR, which basically represent that embedded unit gets the request from display unit to send the data. And when these 2 conditions are met, we have to send the packet with the sequence number 0, and which can be done by triggering this transition TS0. And here we will have to also set the count, the value of the count to is equal to 1 by firing this transition. And after that, a embedded unit has to wait for the acknowledgement with sequence number 0, which can be shown by putting a 0, by putting a token in PSW0. And after that, it may happen that your embedded unit design, or suppose it detects the timeout of the acknowledgement, so which can be done by triggering of TSW0. And once it happens, the acknowledgement timeout can be shown by putting a token in PT0 and 0, and with the semaphore value variable is equal to 0. And then the TS0K at the transition that will show that that the trigger that embedded unit sends the packet with sequence number 0, and this transition is fired only when K is less than n, and subsequently we have to increase the value of the K. And then if it can be possible that your data packet of the sequence number has been sent by putting a token in PS0S, and after that the TCOM1, it basically represent that display unit sends the acknowledgement to the embedded unit with this sequence number 0. So once you are sending the acknowledgement, you also have to tell up to of which sequence number packet you are sending the acknowledgement, because accordingly the has to be taken care. Otherwise, the same sequence number or the sequence number whose acknowledgement has not been has not been got, we have to resend it. And then after that, the acknowledgement number of acknowledgement with sequence number 0 will be received, which can be shown by putting a token in PR1R. And these, because a PSW0 was representing that it is waiting for the acknowledgement, so the token will be pulled out, and the transition that will be fired is known as the TS0 acknowledgement success, which represent that acknowledgement with the sequence number 0 has been received and the data send is also completed successfully. So then we need to put the token into the 3 places. First of all, we have to reset the entire system. And to reset the entire system, we again have to put the token in PDSR, which represent that embedded unit gets a request from display unit to send the data. And one, we have to put a token in PSRDY, and which basically represent that embedded unit is again ready to send the packet with semaphore variable. And the other one, the token needs to be put on the P success, which represent that data send is successful and is reported to the operator. And thereafter, one more point that needs to be addressed, like when your data send is unsuccessful, is reported to the operator. So what you will have to do is when it was timeout of the acknowledgement, and if suppose the count value is also exceeded the n, it will fire a transition TS0 as a acknowledgement and success, which represent that process of data send is terminated without the success of without success after n trials, and this transition is fired when k is greater than or equal to n. And then the PDASU represent when the token will be in this place, it represents the data send is unsuccessful, and it is also reported to the operator. So this is the total function of our model, or specifically the communication module. And one thing we can notice that the left half of this image is the right half of the image, and the reason is because it contains, the reason is, I'm using the two embedded units and the 2 display units, 2 communication protocol because of the because of the redundancy to improve the reliability, and hence alternatively I'm sending the packet from the alternate embedded unit just for the online testability purpose. So one time I'm sending the packet from the left side and one side from the right side. And now the next one is I have to this model I have drawn, and there are the various tools that are available which supports the PatriNet tools. One is the, for example, the TimeNet or the Patri or the CPN. These are the tools, and we have used the TimeNet tool known as so where we have to embed the transition delay in each of the transitions, because we are dealing with the real-time system, and the transition delay can be derived from the statistical data, or you can apply the artificial intelligence where you can make a statistical model, and based on the statistical data, and if it can also refine your statistical model based on the new observation that it may come. And the inputs that can be taken from the statistics as well as the expert elicitation and your design, and accordingly the delay of each of the transitions in seconds has been put, which is shown in the left figure. And then you can do a run of that model, and which will give you the throughput of each of the transition. And the throughput of the transitions are shown in the right figure. And then you can you have to create the reachability graph. And as I said, the reachability graph is very simple, because we have to identify the number of nodes, and number of nodes basically you can go back. So basically from the state nodes represent the states of the system, and which can be represented by the token distribution of the system at particular point of time. So starting at the initial point of time, the token distribution will be like only the token will be are in 2 places, so 1 0 0 0 1 0 0 0, or it will be like this. And so this is the token distribution as represented by M0. And after that, what is happening? This is the transition, this is the transition that will fire, because all of its input places are containing sufficient number of tokens, and when it fires, the movement of these tokens will happen, and one will be deposited in the PS0S, and one will be deposited in PSW0, because the movement of the tokens from input tokens to output, from input places to output places occurs, and will be governed by the weight of the respective arc. And there is no law of conservation of the token that we have already seen. And then so it means the token has been moved out from the earlier places and has been deposited into the new places. And in this way, we can, derive the entire reachability graph, and the constructed reachability graph is not enough. We also have to analyze. Okay, I'll be touching on later, but before that, you can see all the transition rates or the throughputs. Throughputs are known as the transition rates. Transition rates means number of transitions per unit time. So we have just mapped all the transition rates of like lambda 0, lambda S1, lambda SW0 to lambda 1, and so on. And then this is the reachability graph, where you can see all the nodes are representing the states or markings, as we have seen. In the PatriNet model, the states are also known as the marking. And you can see, so from M0, it is the distribution of the token is like this. After transiting S0, it is changing to M1 state, and after M1 state, it is changing to M2 state. Okay, in the same way. So from M2 to M3, and then it can go back to M2. From M2 also it can go back to M1, and like this. So this is the entire reachability graph. You can see, you can make, and it helps in identification of the total states that are possible, as well as the reachable. Why it is a reachability graph? Because it also helps in identifying whether it is possible to reach that one particular state from the existing state or not. And as I said, this as we have already discussed also, how we can transform it into the reachability graph. So we can easily transform we can how into the Markov chain, which is shown in the right side. So all the M0s are nothing but these are the states, and we have just put it, we can represent it by the big circle, by the circles. So these are the M0s, M1, M2s, and so on. And all the lambdas are nothing but these are the transition rates. And now we have to create the transition rate more matrix, and which I have already touched upon. Like Q is a generator matrix or the transition rate matrix, in which in the rows and in the columns we have to write all the states starting from M0 to M9, and in the columns also, and then you have to fill in the elements, the metric elements, which denotes the transition rates from one state to another. For example, the transition rate from, just go back to the Markov chain. You can see the transition rate from M0 to M1 is lambda 1. And so basically M0 to M1 is lambda 1, and rest of all are zeros. But how you can derive the diagonal matrix element, that is N0 to M0? This is very simple, as we have seen the first equation. Just I'm trying to go back into on the same slide. Yeah, this is this equation. So that if I want to calculate the transition rate from state I to state, it would be is equal to minus, and we have to sum up all the transition rate from state I to rest of the state. So what you have to do, just again going back to the same point where we have transited. Yes, so from M0 to M0, it is minus and sum of all the transition rates. So for that, you have to sum up all the transition rates on that particular row. And now, again, go back to this, and you can see from M1, it is transiting to M2 as well as M4 by transition rate lambda 3 and lambda 11 respectively. So you can see from M1 to M1, from M1 to M2, it is a lambda 3. From M1 to M4, it is lambda 4. And the diagonal elements can be computed by minus the sum of all these elements, that is minus lambda 3 minus lambda 11. And in this way, we can, create the entire transformation matrix. And then I have to calculate the transition probability. So the transition probability is calculation is very simple. Suppose I want to calculate the transition probability from state I to J. So that will be equal to the transition rate from I to J, and you have to just normalize this transition rate. So for the normalization, you have to divide it by sum of all the transition rates except this Dij. So this is applicable when j is not equal to I, and if j is equal to I, it will be 0. And this is the transition probability that we got. And now we have to use the two-state equations. Let me go back to the same slide where we were discussing the big container filling of the water, and we have derived the two equations. One is sum of all the state probabilities, state transition probabilities, or sum of all the state probabilities of the system will always be equal to 1. That is from the total probability law. And so this will be is equal to, m, because the states in our case are lying from m0 to m9. So all these you have to add. M0 plus M1 plus M2 up to M9 is equal to 1. And next is this formula. This already we have discussed, and which is basically, which has been put here. So this is what this is. So M0, M1, all these are the state probabilities, and these are the stationary probabilities. And this will be equal to, this is the final state, and because we are dealing with the multiple states, so this is a row matrix, and it will be equal to just the previous state. So it will be equal to M0 to M9. And we have to multiply it by the transition probability. So this is the entire transition probability matrix, because we are not dealing with only one state, and so we have to multiply it by the transition probability matrix. And then you have to solve these two state equations analytically, and which will give you the value of each of the MG states, that is M0, M1, M2, and so on. And this will be the state probabilities. And so after solving the equations, you can find these are the state probabilities. The values are already stated here. And now the next is you have to find what are the good states or what are the bad states. We have already seen the definition, the good states in the sense which can be useful to perform the functional requirements. These are the normal behavioral states, and the failure states are basically those in which your system is getting failed. So either way out is you can sum up all the success state probabilities, and you can sum it up, which will give you the reliability of the overall system. The other way out is you can sum up the failure state probabilities, and you can subtract it by 1 to give the quantification of the overall system reliability. So what you can do, you can just go back to this figure, and you can see this M3 and M8. These are the two states which are basically confronting by the transition of the unsuccessful acknowledgement. It means what is happening? The data package had been sent to the display unit, but display unit is not acknowledging the packet. It means it is not being received by the packet, or It may be also possible it has received, but while sending the acknowledgement got failed. Whatever, but ultimately the source has to confirm whether it has reached to the destination properly or not. And M3 basically it denotes that it has not reached the acknowledgement varies successfully, and hence it is a failure state. And similarly, M8 also, transiting through acknowledgement and success, and you can add on these either the other way out. You can leave these two states because these are the failure states. And for the quantification of the overall system reliability, you can add all the state probabilities of this particular system starting from M0, M1, M2, and so on, leaving M3 and M8 state. Or the other way out is because generally, the behavioral states are many, and these failure states are less. So the other way out is, why don't you add on the uh, failure states, which will give the quantification of the failure reliability of the overall system, and if you will subtract it by 1, that will give you the quantification of the reliability. So you can do, so what we have done is we have just added M3 and M8 state probabilities, and you can subtract it by 1, which will give you the reliability of the this communication protocol. So this we have seen. So what all the things we have seen? First, we have seen what are the essentiality of the safety critical systems, and how these safety critical systems are distributed in nature, and these are the IoT systems, and it is very essential to understand the correct functionality of these systems, so for which we have started finding out the reliability. And because in engineering everything is about the measurement, we cannot rely more on subjectiveness. And for the quantification, we have started from the basic definition, and then we have also with the stochastic that then we have seen also some of the traditional methods to quantify. We have seen the limitations of those models with regard to the stochastic to show the that uh, you know, we have introduced the reliability prediction framework, in which the three are the important phases, in which in the first phase we have to create the net model. Then the second phase we have to convert it into the Markov chain, because internally we can represent, or we can create a reachability graph of these nets, and which can be transformed into the Markov chain, and then we can apply some of the mathematical concepts and the related to the depending on the context of the application, and then we can see like how we can quantify the state probabilities and how we can solve these equations analytically, and then we can see how we can quantify the reliability of the communication module. So we have targeted the communication module, but you can target because the you should know that the reliability of each of the components and the functions are not same. Some may be highly critical, some may be less critical. So you can identify on the critical components, and you can go for such kind of analysis. But because this analysis is costly and it requires the modeling expertise as well as the statistical data also. So, and then the benefits that you will get will overcome your effort, and So this is all about my talk. In case of any doubt, you are happy to ask.